It is often asked if El Nino happens out there in the middle of the ocean, why should we care? Well, obviously, it's of great interest anyways, because even in the ocean it affects the heat uptake and the global warming. Upwelling affected and phytoplankton affected also means fisheries affected and corals affected and life on Galapagos severely affected and so on. But of course, there's a much broader implication. When we move such a large heat source around, waves are set off not only in the ocean but also in the atmosphere, and the circulation Walker cell and the Hadley cell are also perturbed at a very large scale. So we have looked at another version of this already when we did the Bjerknes feedback. So during a La Nina we have larger than normal cold tongue, cooler than normal temperatures extending farther west, and the worm pool getting warmer and crunched together, often rainfall increasing and creating floods over here, whereas during La Nina the convection shifts eastward, creating warm sea surface temperatures, anomalous subsidences over the west and over here, and monsoon over India gets perturbed. And again, as I said, this peak here happens in December, January, February, but monsoon peaks in June, July, August. So depending on how long the El Nino is evolving, remember the moving of warm water from east to west by ocean currents takes a long time, months. So obviously that whole process of how warm water that has accumulated between two El Ninos and during La Ninas is discharged and redistributed takes 9 to 12, sometimes 18 months to finish doing what it does in terms of all these feedbacks that we talked about. So there are many things that are perturbed at different seasons as the El Nino evolves. So here is a demonstration of the dynamical response of the troposphere to El Nino SST forcing, field regression of 300 millibar geopotential height and wind anomalies onto the time series of SST anomalies in the Niño 3.4 region, which is averaged over here. Units of 300 millibar and geopotential height are in meters per standard deviation of variability in the Niño 3.4 index. Positive values indicate anomalous highs and anticyclones. So just like in the ocean we have high sea surface height anomaly means anomalous anticyclonic or clockwise circulation in the northern hemisphere. Anomalous low sea level means counterclockwise or anomalous cyclonic circulation. Same convention works. So you have anomalous anticyclone, anomalous cyclone going all the way over to the North Pacific, on to the North America, over to the Atlantic, and similarly over here into the southern hemisphere. Of course, remembering cyclones and anticyclones are reversed in direction in the southern hemisphere because Coriolis reverses direction. So the perturbed convection heat source is always setting off waves as well as changing the convergence, divergence, subsidence, ascent parts as well. So this is the resulting impacts of El Nino fit for public consumption. Typically NOAA puts out a lot of these images that I'll show in the next chapter. So here is extended Pacific jet stream amplified storm track. So you will end up affecting the cyclogenesis, conditions favorable for cyclone birth, and number of cyclones that will intensify after they are being born. You will get wet conditions here, dry conditions here, warm conditions extending in this direction. So the consequences of all these perturbations can be serious, some good, some not so good. If we take a more global view, you will see that warm episode relations and cold episode relations depend on seasons. Remembering again that El Nino and La Nina peak during December, January, February, but they evolve over time and affect multiple seasons. So during December, January, February, when the El Nino is in peak phase, you have warm temperature anomalies here and dry and warm conditions here, dry and warm, wet conditions here, dry conditions over here, wet and warm here, warmer here, warmer there. So you can see that there are global patterns of rainfall and temperature perturbations all the way, even this is not showing Antarctica and Arctic, but those waves also go into the Arctic. These waves obviously affect the Arctic and the Antarctic as well. Okay, those are also reported in many papers that you can read up. So during the June-August of the El Nino, when it's still evolving, you can see that the monsoon is perturbed here, the Indonesian maritime continent, South China Sea, Philippine rainfall is affected here, the SPCZ and the Australian rainfall and temperatures are affected. Already you have some perturbations to the convection moving eastward, and you have fairly significant impacts also on South America and Central America. The fact that La Nina can last longer than the El Nino, that asymmetry is also obvious in terms of asymmetry in the teleconnections. Because El Nino and La Nina happen here, but the signals are happening here, we call them teleconnections. Okay, it's a cute word that you should remember, like telepathy. Not really. Okay, so December, January, February, you can see that there are cool conditions here, wet and cold conditions here, wetter than normal here, cool, dry than normal here, dry and warm, and so on and so forth. But the pattern here, the main point I would make is that it's not completely in the opposite direction to the same season during an El Nino. So there are also asymmetries in the El Nino and La Nina teleconnections during the season. So during La Nina, India tends to get more rainfall, but not always, and this also is not always. So there are other factors like high latitude connections that play a role as well, but nonetheless. So again, June to August, you can see wet and cool, cool here, wet and cool here, warm here, dry here, and also some signal here. So again, not symmetric to what happens during an El Nino, but nonetheless. And of course, these things don't end in December, January, February. There are other delayed effects, like the Indian Ocean warms into the spring after December, January peak of the El Nino, end of the El Nino, and that warming in the following season can have a feedback to the Pacific, it can have a feedback to the Indian Ocean. So even though the El Nino happens at 2 to 7 year time scales, you can produce other time scales because of the delayed effect. So there are statistical techniques used to extract delayed teleconnections as well. So you should just remember those. Okay, that possibility is there. So this is showing January 22, which is just last month as I'm recording this. There is a La Nina going on, which is extended from 2021. So here is an example of an El Nino lasting multiple years. So you can see colder sea surface temperatures with the so-called tropical instability waves. ITCZ is showing some mesoscale eddies and how convection tends to be organized in little pieces, and you see other anomalies here. So these anomalies in the Pacific tend to be very strong, associated with the El Nino, which relates to a mode called the Pacific Decadal Oscillation, and there is debate about whether the Pacific Decadal Oscillation, which is related to the Aleutian Low, is independent of El Nino and La Nina, or whether it's a lower frequency manifestation of El Nino and La Nina, because El Nino and La Nina reorganize warm and cold temperatures at such large scales, at long time scales, and so on and so forth. So you can follow up on those sorts of details. this is El Nino winters again over North America, and La Nina winters, just showing more details of what we already saw. So I'm not going to dwell on that. But there are also consequences in terms of number of cyclones and hurricanes. So you can see here that you get warm and wet conditions here. So you tend to get more hurricanes due to less vertical wind shear. So the wind from the surface to the upper atmosphere is changed in such a way that the cyclones are not chopped off, so they are allowed to grow more. So you get more typhoons and cyclones, and also similarly here you change the shear in such a way and the temperatures in such a way that you reduce the number of hurricanes in the North Atlantic during a El Nino, but on the other hand you increase them during the La Nina, and similar change happens here during the La Nina. This is showing warm ocean and reduced wind shear. So this is the main cyclogenesis region. So you see how the anomalies that we talked about here can affect the series of processes like cyclogenesis, intensification of the cyclones, number of cyclones that will survive to grow to greater categories, number of them that make landfall because of the steering wind changes and so on, are all affected by El Nino and La Nina. So to summarize the different processes by which El Nino impacts the global atmospheric carbon dioxide concentrations, including whether it leads to more or less atmospheric CO2, here you have to use your physical oceanography knowledge of trade winds creating Ekman divergence, and vertical profile is such that colder, higher pressure waters below the surface have more carbon dioxide in them, like a cold sealed can of Coke. When you open the Coke, you release the CO2. Similarly, upwelling is constantly bringing up cold, high CO2 waters close to the surface, and it is being released to the atmosphere. So when you reduce the upwelling during El Nino, you are keeping that colder, deeper water below the surface. So you're reducing the outgassing of CO2 from the ocean to the atmosphere. So change during El Nino is that CO2 is less soluble in warm waters, so impact on atmospheric CO2 concentration is more because you are absorbing less biological productivity, so that means photosynthesis is not taking up CO2, so you are increasing atmospheric CO2 relatively speaking. Less upwelling of CO2 rich water, so you are releasing less to the atmosphere, so the impact on atmospheric CO2 is reduced. Droughts and wildfires are created by all these teleconnections that we saw, which on an average, there are regions which get more rain like East Africa during an El Nino, but there are many more regions like the Indian and northeastern Brazil, African regions, Australia, Indonesia, which get less rain. So there is more droughts and wildfires, dust storms and so on, which increase the CO2 concentration in the atmosphere. Okay, so that's the summary. So I'll come back and conclude with the other zonal modes of variability in the tropics, in the Indian Ocean and in the Atlantic Ocean, some of which also have, or at least argued to have, teleconnections, even though they are not as strong and they don't last as long as El Nino, and we'll see why that is. Okay.